for me, technologically, practically speaking, that's why this discussion matters so much, is because if we don't understand how the star is fusing atoms together and generating all that power, I mean, you can't even look at the sun, it's so powerful. We're not going to have any hope of pulling that off on Earth. And there does seem to be an approach to fusion on Earth that is promising, that involves lattice confinement of fuel sources.
It's not only that you can weaponize it, but you completely undermine the entire geopolitical system that's based on alliances around the securing of energy resources and the maintenance of all of those supplies. Like, if you end up in a position where petrochemicals are no longer the foundation of the entire geopolitical system, like, what happens to the way that the world is organized?
And back to the state crafting, right? Like, if somebody does understand how to do this properly, if somebody deep inside the state understands what we're saying, which is actually obvious to anybody with a prism, you can explain this to 14-year-olds, in freshmen in high school. If somebody deep inside the state understands that and they are pursuing lattice confined fusion, it's probably quite profitable that everybody else in the world doesn't understand it, right? So there's potentially an incentive aligned with keeping that knowledge below board.
Chris Lehto, welcome to Lehto Files.
Hey, welcome to Lehto Files. Today I'm talking with Dr. Michael Shilo Delay and Dr. Anastasia Bendebury, the hosts of DemystifySci podcast. Both have PhDs from Columbia University, Dr. Bendebury in bioelectricity and Dr. Delay in molecular water physics. After leaving academia, they launched DemystifySci to explore fundamental scientific questions. They challenge mainstream narratives and make complex topics more accessible. We'll dive into their views on modern physics, scientific gatekeeping, and how it relates to UAP. So thank you guys so much for being here. How are you doing today?
Super stoked to be here, Chris. Thanks for having us, man.
Really good.
Okay, excellent. So what was the main motivation behind starting DemystifySci?
Well, we finished graduate school and realized that conventional science forces you into a really discrete path. Usually, when you come across somebody who has a career and you figure out, well, how did you get into this? It's that they studied this thing in grad school, and then they continued for the rest of their career to kind of get deeper and deeper and deeper into the subject. And Shilo and I are generalists. We like the practice of science. We realized that there was so much that was getting passed over and ignored and thrown to the sidelines because there's these really, really strong conventional narratives that some theory is consensus and we figured it out and this is the truth and we're always going to think this. And we kind of looked around and we just saw all of these ideas that were getting unfairly maligned, especially in physics.
Yeah, I had a super naive perspective. Like, I figured, if I work my way to the top of the academic pyramid, that somebody would have the answers to all these things that were driving me nuts since I was a little kid, basic stuff like electricity, magnetism, gravity, stuff that affects us all the time in our daily lives. And I met a lot of my heroes when I got to Columbia, and I just had my disillusionment,
Don't meet your heroes.
Crisis. Yeah. So yeah, we just love calling people up and talking to weirdos, academics. It doesn't matter. Anybody who has a really coherent theory of how something works, we're listening.
Mostly because we were looking at the world and we were like, well, 50 years ago, we had a lot of ideas about the way that nature worked that were pretty far off base. And then if you go even farther back, you start to get into really totally off the wall ideas. And the threads, the seeds of the ideas that we think are correct now were already around 100 years ago, but nobody was paying attention to them. And so we were kind of like, okay, well, what if we could go out and we could find the ideas that are going to be the ones that are more correct than the ones that we have today?
It seems like we're always wrong, right? Every model we've ever had or ever come up with has turned out to be fundamentally wrong on some level. It seems to work for our knowledge base at the time, But then as we learn more about the universe, that model doesn't work anymore. So it seems like we're always wrong in the past, and yet our current science believes that we're correct, right? That we have all of the information, even though, like you mentioned, you look back in the past, all of our views have changed.
There's a weird element of statecrafting involved in science in the modern era, too. And when you have an authority structure that's pointing to science, they have to, in some sense, defend that it is 100% correct. And people expect that their state structure is going to guarantee them answers to everything, it turns out, including the birth of the universe. So I think it's understandable in the modern era. And I think that before that, perhaps the church would have taken that mantle upon themselves. But science is obviously designed to continually update its catalog of explanations for the universe. That's really how it's supposed to work. And then once the state gets a hold of it, it becomes some whole other ball of wax.
They just ruin it. So, what do you think is the biggest misconception in modern physics that needs to be corrected? You mentioned the Big Bang and you're making a conference this summer aimed at it. What's the biggest misconception?
I think that it boils down to a fundamental misconception about quantum physics. And quantum physics seems kind of deeply unrelated to the Big Bang because they're kind of opposite scales. One is the tiniest structure possible, the other is everything. But there's this really fascinating history of people trying to figure out how stuff like electricity and magnetism works, where they, for a long time, pursued a material explanation, where they were trying to figure out, okay, well, what is causing electricity? What is causing magnetism? Why are they related to one another in this orthogonal way? And Faraday was kind of the guy we point to as being the progenitor of all of our understandings of electricity and magnetism, right? He was the one who did all of the chemistry studies, and he was looking at the physical properties of these devices and discovering that they were emanating these strange things. And Faraday in his research was really preoccupied with trying to understand how it was possible that these objects were able to perform feats at a distance. And he was desperate to come up with some kind of physical explanation for it, but he couldn't. And at the end of the day, his mentor was this guy named Davies. And Davies was a fellow of the Royal Society, and he was an atomist. And so because he was a chemist, he was studying molecules. And they were trying to figure out why it was that certain chemical compounds could be formed and others couldn't, right? You put things together into a reaction vessel. Some things will never react, other things will react. And they kind of came up with this model of the atom. It's called the Boscovich model of the atom, which is the same one that we use today, which said that there wasn't actually anything at the heart of the atom. The center of the atom was a mathematical point, and it was surrounded by these lines of force with varying degrees of intensity. So sort of this undulating sine wave of these lines of force. And the chemical compounds that were able to be formed were formed because of the compatibility of the lines of force of the various atoms. And so it was this field-based understanding of chemistry. And when Faraday discovered that he couldn't figure out what was causing electricity and magnetism, he kind of fell back on this field-based idea where he was oh, well, everything is fields. It's this invisible mathematical definition of space. And that problem, that definition of fields directly relates to the Big Bang because of the way that we study the light that comes from it, because of the way that we study light from stars. And Shilo has a really good way of explaining this black body problem that has to do with this field effect.
Yeah,
Sure.
I think the fundamental problem is about stars, honestly. And this is what I think might be really exciting for your viewers, and we can get into it as deep as you want. But if we don't understand how stars work, and I think there's good reason to believe that there's a huge misconception about that, which, like Nastia said, comes down to understanding how light works and interpreting light. But if we don't understand how stars work, then The reason that we see these fusion headlines that always point to fusion being 10 years away is because we're going about it completely wrong on the basis of trying to recreate a star with a really bad misunderstanding of how stars function.
So,
And
how do you
we think
think it's misunderstood?
so. There's a gentleman, excuse me, there's a gentleman, a former scion of technology who developed one of the most impressive MRI machines of all time at Ohio State. And he was a chair of the Department of Radiology, I believe it was radiology, for many years at Ohio State University. And, the funny thing about radiology and about MRI machines is that you're essentially looking at light coming back to you in various ways from human bodies. And so this is a man with very intimate knowledge of light reactions and interpreting radio signals of light. And he turned his attention to the solar spectrum at some points. And he made a really astonishing discovery, which is something that had been discussed heavily back in the 1800s at the Royal Society, which was, wait a second. The light that's coming off the sun, if you split it through a prism, you see a very beautiful rainbow of colors. However, we're told that the sun is a burning ball of gaseous plasma. Now, the problem with that story of it being a burning ball of gaseous plasma is that when you split gaseous plasma through a prism, you don't see a beautiful rainbow of colors.
No,
You
discrete
actually,
line.
exactly, you see individual lines, right? Because individual atoms in a plasma, in a gas, they can only vibrate. They can only vibrate in a few ways. You think of like a droplet of water that's just floating in free space. It has a few axes that it can vibrate on. But when you marry it to other droplets, right, when you have lots of atoms in a lattice, you actually multiply the vibrational modes for that light in such a way that you honestly can generate an infinite number of overtones as a result of that, near infinite, right? And the result is this beautiful continuous spectrum that we call a black body spectrum. And you can actually get this continuous spectrum by heating up any liquid or solid on Earth. You can make a nice black body spectrum. They used to use soot-covered chambers originally because they're extremely opaque. And so they have this maximum emission and absorption quality. And so all this work was done about black bodies. They have this very beautiful fingerprint. It's not just a rainbow, by the way. It's a very specific rainbow that has a nice shape to it in terms of the different colors that are emitted. And the weird thing is, those same equations that we use for describing black body radiation somehow got misapplied to the expectation that gases would do the same thing. So back in the 1800s, when this dude named Kirchhoff was developing all of this work about black bodies, he really wanted his equations to apply to everything in the world, right? All the physicists have this dream of these theories of everything, this unification, this universalization of their ideas. And so he tried really hard to fit gases into his black body work. And people kind of ran with it. There was interesting evidence at the time that if you pressurized gases, that those lines we're talking about, those individual frequencies, would broaden a little bit. And, one thing led to another. I don't know how deep you want to get into that history, but there was every reason to believe and be hopeful that perhaps gases might be able to do this black body thing under the right conditions. And then over the next 100 years, it just became baked into the assumption cake of how stars work, that they do all these myriad processes that somehow result in this same fingerprint that we see from heated solids and liquids on Earth. We've never seen that happen in a laboratory, but it should be able to happen in a star. And the result is cataclysmic for everything downstream of astrophysics, because when a star is a liquid versus being a gas, you tell very, very different stories about the life and death of that star. Everything from the formation to the way that it dies is completely, completely different. And so it's a wild ride that, of course, informs the way that we interpret everything about the Big Bang. And of course, this thing that really introduced cosmology to mainstream science, which is called the cosmic microwave background radiation. It was discovered in the I think late 50s, early 60s, and it was quickly heralded as this proof of the beginning of the universe. But the funny thing about that is it's also a perfect black body spectrum, and it's supposed to be from this gaseous plasma at the beginning of time. And so once again, if gaseous plasmas can't make black body spectrums, and we've never seen them do it before in a laboratory, and the only thing you can point to is stars, and stars only do it on the back of marrying dozens and dozens of different phenomena together in order to somehow get this fingerprint to pop out on the other side, then that microwave background radiation probably has nothing to do with the beginning of the universe, certainly has nothing to do with gaseous plasma, and it might not even be cosmic at all. So that's kind of the card at the bottom of the house of cards, as far as I can tell.
Excellent. And that's Dr. Rubier? How do you say?
Sorry, that's Pierre-Marie Robitaille, who's done all the work.
Robitaille, sorry, Robitaille, yes.
His channel's Sky Scholar, if anybody wants to check it out. He goes extremely deep on all those ideas.
Excellent. I know Alexander Unzicker has also covered that, showing that the sun has a perfect black body radiation. Also quite interesting is the temperature profile. So if the sun was really a plasma, then it should be much, much, much hotter than it is, where they talk about the surface of the sun is only, I think it's 10,000 Kelvin, but if it was a plasma, it should be up much higher. So the temperature profile also doesn't match. Instead, it matches what you mentioned there, black body radiation profile, which we still have no real good answer for why black body radiation exists. That's where Planck became famous. That's where he basically determined that there are discrete levels to the atom, was basically through his black body radiation experiments, right? That's how he determined that we have discrete atomic
That's where the
orbitals.
The photon pops out from all that work, exactly.
And a photon randomly is made up, right? But we've never actually observed a photon. You've never observed a photon. We've seen it, it's like dark matter or dark energy. We see the effects of something and we make up or we postulate that a photon causes this, but we've never actually physically detected a photon. We detected the results of a photon, or we detected the results of dark matter, right? What dark matter would explain it, as well as a photon would explain what we're seeing, but we've never actually detected a photon in it.
Many have claimed that they do, though. It's worth mentioning. Many have claimed, but you're right. They're ultimately interpreting the detectors in their system.
But this is what I was trying to say about the field effects, is that I think that the fundamental problem is that there is a physical material explanation for what we're observing. Like what Shilo was saying about, okay, so the black body curve has a very specific shape. And that specific shape doesn't have anything to do with the shape of the object that's being heated. It has to do with the material properties of lattices, where you can imagine light as a vibration of the atom. And so which is why like the gases produce these linear spectra. And when you have a lattice, there's harmonics that are able to be generated in the lattice of these different energies that produce the different colors and the different kinds of light. And so if you rely on this field-based world where there's just kind of these electromagnetic waves that emerge from the universe that are not really tied to the atomic structure that lies underneath it, you can get down a rabbit hole of saying crazy things. And you see people basing their ideas off of an immaterial quantum physics, where you can say that, oh, well, the reason that the sun gives a black body spectrum isn't because there's anything materially inside of it that's producing it. It's because you have this immaterial process of these photons just kind of bouncing around eternally inside of the sun for millions of years, and then they happen to emerge at the surface in this perfect shape, and you're like, shouldn't we be thinking about this structurally? Shouldn't we be thinking about this from the beginning of like, okay, well, what are the atoms doing to produce this, both in the sun and in the CMB? But I think that because the CMB was discovered at the height of quantum physics, at the height of this like mid-century scientific project, the immaterial nature of it lent itself to seeing this fingerprint and then being able to say that, like, oh my God, the world is so crazy, the universe is so insane, nothing can really be fully understood. We can easily transpose these ideas onto each other to fulfill the desire to prove that there was a beginning and we have found it.
Like, I don't think people understand how magical mathematics is. You can, like, the equations that they cobbled together to give a black body spectrum, there's nothing wrong with the math there. They're very brilliantly cobbled together, honestly. But so was Ptolemy's solar system, right?
Yep.
This system
Yep.
of epicycles and difference, it was very predictive. It was super rigorous mathematically.
Very accurate, right? That's what they say.
Accurate.
It's
But
quantum
wrong.
field theory is extremely accurate.
But totally wrong, right? Because and the reason that we think that it's wrong now is because there's a more elegant way of describing that in terms of the motion of those bodies. And there's still problems, with that by degrees in terms of what the heck this gravity stuff is and everything. But at the end of the day, having really tight mathematics isn't sufficient to explain something. Mathematics is only a descriptive tool. It doesn't ever tell you how something happens, what causes it to happen. It can only relate your parameters to one another depending on how you're looking at it. And so I think people get really confused about that because, really smart people did all of this work. And I have a great deal of respect for the work that they've done. And I can totally understand how you can be misled by beautiful mathematics. I've been there before. But at the end of the day, nature doesn't care. Nature just does its thing. And so you got to go looking for true cause of these phenomena, especially in physics.
So have you heard of ball lightning? Do you know anything about ball lightning? It's basically
A little bit. Seen some videos.
because we've seen I was up in Hessdalen, and Hessdalen's a famous place for UAP lights. I don't know if you've heard of it. But they have spectrometers.
Is this in like Norway or something?
Yeah, it is. It's Hessdalen Valley in central Norway. I've been up there twice now. Yeah, it's amazing spot. And they, for decades now, they've had called the Hessdalen Lights. They also have a lot of other experiencers, people who say they've seen objects, they have ghost rockets, etc. So I've been up there a few times, and they have spectrometers actually. And what they've said is that these lights will give a full spectrum. So what they're not seeing is discrete lines like you would see from a plasma. So I was curious if your take, could it be ball lightning if they're seeing a full black body spectrum, or what do you think it could possibly be?
Sounds like a material body or a liquid, honestly. I just don't think there's any reason to believe that anything other than a solid lattice or a liquid lattice. The only difference between a liquid and a solid is the transientness of the lattice. So whether the atoms are being swapped out for pieces of that lattice or not. But yeah, I don't see how you could possibly generate it, even from first principles, but also from laboratory experience. No one's ever gotten anything close to a black body from a gaseous plasma in a laboratory.
Oh my gosh, that's amazing. And so Robitaille, if I remember correctly, he says it is H2, right? It's a liquid helium. Is his hypothesis?
It's a hydrogen.
Or what?
Yeah.
I'm sorry, liquid hydrogen. Yeah, H2, liquid
H2
hydrogen.
is actually the molecular version. This would be one of the things, I mean, just to back this up a little bit, back in the late 1800s when they really developed the gaseous sun, there was a bunch of incredible work done by this gentleman named Andrews at the time with the phase diagram of hydrogen. And he was trying to pressurize it in the best way he could. And he didn't have access to the kinds of pressures that we have in the laboratory today. And he thought that no matter how much you pressurized hydrogen, it would always stay a gas. Now, we know that's not the case today. We know that with sufficient temperatures and pressures, we can open up a whole new arm of the phase diagram. And we actually discovered that hydrogen forms a liquid metallic substance at certain pressures and temperatures. Now, we know it's suspected at least to be the case inside of giant planets like Jupiter. And this has been increasingly revealed as an important part of understanding how those giant planets work. Problem is, nobody's really applied it to the sun, even though the sun at certain depths certainly has access to those pressures and temperatures. And there's also this incredible realization that liquid metallic hydrogen is metastable, which means that once you form it, it can bubble up to less pressures and still remain in that liquid metallic form. And so there's a perfect mechanism for what's going on and in the phase diagram at the surface of the sun. You have these roiling convection, bubbling situations. We see these at the surface of the sun. And we have every reason to believe that it is indeed this very nice layered version of liquid metallic hydrogen. It's layered very similarly to the way that graphene is layered, and it behaves optically very similarly as well. So Pierre's done an incredible job of publishing on all of this, and he's being taken seriously by some important people too recently. He was recently given a shout out in this huge plasma review by one of the biggest plasma physicists in the universe right now, as far as we know, this lady named Bogart. And I don't know, I could see this really turning around in the near future. It's just gonna, it's gonna result in a ton of work to be done. And it's really a matter of whether the mainstream scientists look at that as exciting or whether they feel shameful about having, missed the boat for 100 years. And I hope they pick the former.
And he's going to be at the conference this summer, right? DemystifySci.
Pierre's not going to be there.
Oh, he isn't. Oh, shoot. Okay.
He was at our first conference.
But we have two people that are presenting his ideas. So Shilo is going to give a talk on it. And we also have Patrick Van Reyes, who's a plasma physicist, and he's been really into Pierre's ideas. So they will be.
Hunziker's written a book on the liquid sun too. Gareth Samuel from See the Pattern over on YouTube, he's done some work on it. So we're going to have his ideas. I've been on the phone with him constantly, trying to make sure that I got all the pieces. I would really like to know everything Pierre knows by the time that I walk into that conference, because obviously we're going to have a lot of mainstream cosmologists there too. So it's going to be interesting.
Just for my audience, so phase transition diagrams, it's basically a diagram like think of for water, and at certain temperatures and pressure, it's going to be a gas, it's going to be a liquid and a solid. And you mentioned there you have a metastable material. You can think of iced tea, right? So if you imagine, like, how do you make super sweet, like Southern sweet tea, right? You actually have to heat the tea up very hot, and then you can add tons of sugar, right? And then you cool it down. So and what happens is the sugar will stay in suspension. It's like a super solution, maybe. I can't remember the actual technical term.
Super saturated?
Maybe? Super saturation. Yeah, because if you had the tea cold already, you're not going to be able to get that much sugar into the sweet tea, right? That's why sweet tea is so sweet, is because it's hot when you actually mix in the sugar, and then it cools. Actually, you can maintain that. So those are basically the concepts you mentioned there about this liquid hydrogen. It'll form into some sort of a lattice, which will give off a black body signature. So, but there's a standard model, right? When you look at it, it seems like the standard model of the sun has an answer to everything. What do they say to this liquid hydrogen theory, or what's their argument against it?
I think they're catching up to it, to be honest with you. I'm super optimistic about this, and I teach a very mainstream astrophysics course at the university here in Oregon, and I put the models side by side continually, and all the work that we do, all the lectures and everything. And every year that I teach it, I find that the mainstream position is creeping closer and closer. Even this word plasma, for instance, right? The funny thing is, this liquid metallic hydrogen that we're talking about, it can also be treated as a plasma. It's a different kind of plasma than the one that has been advocated, which is a gaseous plasma for the sun. But it's still technically a plasma. It has delocalized electrons. It basically follows all of the blanket ideas that we would consider for a plasma.
So it's magnetic, right? Then, delocalized electrons.
Yeah, absolutely.
And conductive, right? Like any metal. So that's where you get the metallic when you say it's liquid metallic hydrogen. That's why, because it has delocalized electrons.
Yes.
I see that it's a fairly small jump from the way that we already conceive of plasma to saying that, well, maybe it's a structured plasma. And I think that that's the coup that's going to happen, which you see in science periodically, where I don't know if you remember, but for a long time, whenever people talked about hydrocarbons in the earth, they called them fossil fuels. And then gradually we started finding huge amounts of hydrocarbons spread throughout the solar system. And people started realizing that, well, if they're on like Europa and Enceladus, they can't really be fossilized products. And so you never,
Titan's got lakes of these things.
yeah, and like you never hear anybody talking about fossil fuels anymore because there is this recognition of like, oh,
Huh.
this might actually be an abiotic process. But no one gave a press conference when they were like, well, we were potentially incorrect about the formation of hydrocarbons on the planet. And so now we are officially changing the way that we call them to something else. It's just this.
It's not just semantics though. Like I want to be very clear about that. You actually have real world ramifications from treating the sun as a gaseous plasma versus a liquid plasma. Actually matters a lot, especially when it comes to the pursuit of fusion power on Earth. And I think that's really important. I kind of wish we'd brought it up earlier because I think that's, for me, technologically, practically speaking, that's why this discussion matters so much, is because if we don't understand how the star is fusing atoms together and generating all that power, I mean, you can't even look at the sun, it's so powerful. We're not going to have any hope of pulling that off on Earth. And there does seem to be an approach to fusion on Earth that is promising, that involves lattice confinement of fuel sources. And NASA's done a few preliminary studies on this. They're being very tight-lipped about it. We've reached out to them many, many times to get somebody on the show to talk to us about it. They will not do it. And we've had plenty of NASA scientists on the show before. So I personally think that people on the inside know what's up a little bit better than what's happening above the surface in the mainstream. But it seems absolutely possible to fuse substrates together, let's say hydrogens at least, heavy hydrogens, by just confining them within a lattice and applying a little, a little bit of pressure, squeezing them with a laser, let's say, squeezing that metal substrate with a laser. And you can do this at room temperature too. This doesn't require 10 million Kelvin like you need at the center of the sun or in these tokamak reactors with gaseous plasma in order to produce fusion. So it's very interesting and very promising. And the biggest problem with fusion research is obviously keeping that gaseous plasma still, like holding it in place with a bunch of magnets, right? They've been able to do fusion at these extraordinary temperatures in the lab, but they can't keep it stable. They can't keep this reaction going because confining gaseous plasma is really, really difficult.
And this might actually be one of the reasons that it's going to take a really long time for the models to change. Because if you think about how much money has been pumped into fusion research and how much these facilities cost and how central they've been to the government science program for decades, to go back on that and to say, hey, we've spent billions on a technology that has no chance of ever happening is just beyond the pale.
And back to the state crafting, right? Like, if somebody does understand how to do this properly, if somebody deep inside the state understands what we're saying, which is actually obvious to anybody with a prism, you can explain this to 14-year-olds, in freshmen in high school. If somebody deep inside the state understands that and they are pursuing lattice confined fusion, it's probably quite profitable that everybody else in the world doesn't understand it, right? So there's potentially an incentive aligned with keeping that knowledge below board.
That's been the main argument, or one main argument why they will not admit that there are UAPs or that there's even the possibility of a non-human intelligence here. Because we've been asking, all these whistleblowers over the decades come out. Why will the security state, if it is true, if it's all true, and there's many hundreds of people, thousands say it is true, why will they not just admit that there is a non-human intelligence or that there could be aliens here? They don't have to tell us all the secrets. They don't have to give away any of the technology, but just admit that they are here. And my own personal speculation is what you said there is that would immediately change the paradigm. And if the underlying fundamentals are simple, meaning if it is simple, in fact, to create room temperature fusion, now you're talking about essentially nuclear power to anyone around the world that has the really the basics of this technology, meaning it's so simple that the reason they will not admit anything is because now all of a sudden everyone around the world, including your rogue actors, your nation states that we don't agree with, our adversaries, can immediately get access to essentially unlimited power, which you could then obviously weaponize, right? So do you think that's possible? It sounds like.
It's not only that you can weaponize it, but you completely undermine the entire geopolitical system that's based on alliances around the securing of energy resources and the maintenance of all of those supplies. Like, if you end up in a position where petrochemicals are no longer the foundation of the entire geopolitical system, like, what happens to the way that the world is organized?
Like, this might need to be done carefully. I'm always, whenever people start talking about how the deep state is interfering in all of these geopolitical arenas and so forth, you got to step back and be like, wait a second, we're enjoying this comfy standard of living here in America largely because of the dastardly moves by our secret covert intelligence agencies all around the world. And like, I hope that we can do that in the future without having to knock each other's knees out geopolitically. But a transition like this probably does need to be enacted very carefully in order to not disrupt the entire world economy.
Yeah, that's. I think that's been their main argument, right? When they say national security, you kind of just hit the national security right in the knee. If you imagine the current world order is, fully led by the U.S. and the West, and so I think they have a huge incentive to not share any of this information. We've also heard about there is a controlled disclosure plan. There's like a schedule where they're trying to, you know, slowly leak this information out. But I don't know if it's going very well. Personally, I think that lying and cheating and stealing is not worth the great standard of living that we have. I moved overseas, and standard of living overseas is great. Like, very nice. It's safer than the U.S. Hate to say it, but Portugal is safer. It's very nice. So I don't know. I think it comes back to our shores. All the evil, dastardly things we do in the name of national security and fear, I think in the end will just come back to us. If we're going to sacrifice our integrity because we're scared of what's going to happen, scared of giving up all our power and our fancy toys, I think it just comes back to hurt us.
I've wondered a lot about other countries' role in investigating UAPs and non-human intelligence. Like, there are other powers. China, Russia, India. Are there programs of disclosure or any kind of indication that people are working on it in those countries, or that that's even really a topic of conversation, or is it mostly just in the United States?
No, it's definitely overseas. So there's multiple countries have said that they believe in NHI. The UK released their basically Condon report in 2000, I believe. France has released the Cometa report, and then David Grush recently said in his whistleblower accounts that there is a behind the scenes Cold War going on, basically an arms race to try and get access to this technology, get access to this information. Whoever can get to cold fusion first, I guess, that can understand it and control it, will rule the next century or something. But yeah, he said for sure China and Russia, he named, have their own programs, and behind the scenes, he said that they do know about the existence of non-human intelligence. This is again his words, and that there is a Cold War to try and get a hold of all this technology, which he said is very bad, right? So it's very bad that there is a behind the scenes covert war going on, and it's really, again, nothing is transparent. So if we don't know what's going on, if the rest of the world doesn't actually know what's going on, then you could get into some really dangerous situations where one nation is really scared for their own survival or future survival, et cetera, and maybe they instigate a war or something based on information that the rest of us don't know.
Mm, it's grim.
It's grim.
It's very grim.
I'm
I don't know.
excited though. Yeah.
Yeah.
Yeah. I think we're seeing great breakthroughs. So let's move on. I guess you've interviewed a lot of experts, like you mentioned, a lot of independent thinkers. You have a interesting forum going on tonight where you're going to have theorists come on and give their pitch their ideas. So, what's the most compelling idea you've encountered that challenges mainstream science? Is it this sun model?
Probably for me, probably, and only we didn't talk about the academic fallouts of such a model too, and I think that's we talked about the fusion, which I think is actually the most important piece, but I think one of the things that will prevent this from happening overnight is the downstream consequences on astrophysics and cosmology of adopting a liquid sun. And it seems rather innocuous, and we tried to sort of give them an olive branch about how this weird plasma can be saved. But the reality is that liquids are incompressible, essentially. At least they're highly resistant to compression. And so the entire downstream gravitational collapse story of what happens to a star at the end of its life goes out the window with the gaseous sun. So does singularities and a lot of the Big Bang architecture.
And like all the weird stars too, right?
Lots, yeah, like everything from white dwarfs to neutron stars, they have a new interpretation available that's rather mundane by comparison. Black holes, there's a rather mundane interpretation for what's happening there that has nothing to do with ultra compact objects.
Mm.
And so, that's really troubling, I think, because there are huge societies built on the back of speculating and theorizing and mathematizing these ultra compact objects, everything from white dwarfs to black holes to singularities to the Big Bang. This is a huge, dare I say, industry, but it's an academic industry. It's a huge corner of academia that has just ballooned, just blossomed in the past 50, 70 years. To say goodbye to that, or to try to reorient all those people to the new issues that will need to be developed, I'm going to be optimistic. That's a huge ask, and I think that's a ridiculous amount of inertia to face in terms of us as proponents of the liquid sun. We're going to have to expect a lot of hand-holding to get through that transition.
Would this mean like the electric universe is correct? Is that different from what Eric Lerner is proposing? Because he will be at the conference this summer. So would that change?
Eric will be there. I'm super stoked to hang out with Eric. I've met up with him. We've both met up with him in New York when we were in school there, and he kind of got me down this rabbit hole when I was a little kid too. I read his book and got really stoked about there being understandable explanations, right? I've personally moved on a bit from the electric universe perspective of Hannes Alphen. He's definitely a brilliant man and has brilliant insight. But the cool thing that Eric brought to the table with that book was the basic idea that the universe doesn't have to be this incomprehensible story. It doesn't have to involve impossible to imagine zero-dimensional objects. There are alternative explanations that children can understand, that
And his
your
book
parents can
was
understand.
the Big Bang didn't happen or doesn't exist?
Never happened.
Never happened. Okay, sorry.
Yeah, I mean, I think that I want to get back to this question of like the other interesting theories that we've encountered, because I think that the liquid sun is a huge one, and I'll get back to it in a second. But with Eric and the plasmic universe, I think that the point that he makes is a really valuable one about the role of mysticism versus comprehension. And I think that especially if people don't read his book, that's fine. You should read at least the first chapter. Because in the first chapter, he makes this really beautiful historical analysis where he says that societies tend to oscillate between periods of a well-informed priest class that keeps the secrets and then this dispersal of knowledge to the people that are empowered to make sense of the world themselves. And everything that Shilo is pointing to right now, everything from the Big Bang to quantum physics, belongs to the priest class that says, there are impossible things that you cannot possibly understand,
It's too
and we will
complicated.
tell you that they are. It's too complicated. It's too complicated. Mortal minds cannot understand. It blows my mind. Neil deGrasse Tyson wrote a book called, I think, like Astrophysics for People in a Hurry, and the epigraph of the book is his own quote, which I find hilarious. But the quote is, "The universe is under no obligation to make sense to you." And I'm like, that is atrocious. You cannot, as a scientist, you cannot, as a philosopher,
As a culture.
as a culture, say that the universe is not meant to make sense to you, because then you live in a world where somebody can tell you something that makes no sense. This is like, how old is the story of the emperor has no clothes? Or it's
Emperor's New Clothes?
Emperor's New Yeah, the Emperor's New Clothes. I think that the story is well known. It's been around for forever, but there's this key piece of the story that is often forgotten, which is, well, why does the emperor end up in the street naked for a child to be the one to point out that he's naked? It's because he's told that the clothes can only be seen by smart people. And so he convinces him, he doesn't want to admit that he's not smart. And so he's like, oh, yes, I can see these fine robes, of course. And then the story unfolds. And it's like, if you live in a society where you're surrounded by people that are saying things that make no sense, and they're all telling you that, hey, it's okay that it doesn't make sense because you're just not smart enough to understand, you go down this rabbit hole of complete and utter chaos.
Which we see.
I mean, yeah, in the worst case scenario, you actually open yourself up to being taken advantage of by the toughest, meanest person who's willing to take authority of the society or of the culture and just tell you that, you're not capable of understanding what I'm doing, whether it's whatever dastardly plans they have, whether it's everything from mass murder to taking your rights away, they know better than you.
Yeah.
And you're not smart enough, so get out of my way. And you just accept it because you've been conditioned as a culture to accept that there's people that are smart and there's everybody else like you. And I think that humans, by and large, are actually quite smart, at least capable of understanding physical reality at the bare minimum. There's no way we made it millions of years down the evolutionary pipeline without being able to comprehend our physical reality. So it's just a really scary state of affairs from a cultural, sociological perspective when we're willing to accept these emperor's new clothes gods of science at the top telling us that we're just too dumb to, comprehend the mathematics or something.
Yeah, they have extremely complicated systems. There's 37 free parameters. You have quantum field theory with which has separate actual fields, right? You have a field for
Whatever
each.
that is.
Yeah, whatever that is, right? The Higgs boson operates in its own field. It doesn't interact with other fields. You have the proton field, the electron field. I mean, it sounds exactly like the geocentric model where they had, Mars had its own field, the moon had its own field, the sun had its own field, and they didn't interact. And the only one that could understand was the priest class who had the knowledge of the physics or the math that they essentially invented, right, to explain this concept. And what happened is the fundamental underlying perspective changed. And now you can explain it to everybody. Actually, no, the sun's at the center of the solar system and our little planets go around. You can explain it to a little kid, right? Like you just said, like the kid, you can explain it to them. You don't have to teach them epicycles. You don't have to teach them Fourier transforms now to explain the concept to them because you have a better understanding of the fundamental reality. So my hope is we'll see that very soon with quantum field theory, right? They invented math essentially, right? Imaginary numbers, I believe, were invented to explain quantum mechanics, etc. And it's very accurate, just like the old Ptolemaic models. But what happens when we get a better understanding, a better fundamental understanding? Will that change all of this? So now people will be able to understand it because we have a better fundamental understanding. do you think the liquid sun model could actually do that? Because I don't understand how it could relate to like quantum mechanics or the misunderstanding in quantum mechanics.
I mean, we have a separate project going on that actually got us into YouTubing in the first place. We have a tiny little channel where we explore material solutions to atomic phenomena. So we try to actually materially interpret quantum mechanics. So how in the world does one atom interact with another atom at a distance? And what we do is we go back to the fundamental mathematics of quantum mechanics and we interpret it as describing the motion of different parts of the atom. So we build out a version of the atom that is a little bit more what we think of as refined than the traditional, shells that chemistry gives us. There's a nucleus, there's these electron shells stuck on top. We make the fundamental observation that actually, if you look at the location of the electron in its shell, in a simple atom like a hydrogen, for instance, the electron can usually be detected at some given distance from the nucleus. We call that the shell, the electron shell in chemistry. But the equation actually says that that electron can be detected at any distance from the nucleus. It's just more likely to be detected at the shell. But the result of that you can interpret is that the atom actually has an extended architecture. It's kind of furry in a sense. In other words, there are some sort of projections that reach out and are capable of interacting with its neighbors. And once you make that realization, then you're in a whole new ball game because you have the ability through relay networks to actually affect all of the different motions at the surface of each atom across vast distances without having to invoke magical forces or cue up Star Wars soundtracks, that kind of thing. So we've been working on that for a long time. We're actually working on a book right now. Hopefully it'll be out later this year about this material atomics approach. And in some sense, what Pierre's done with the liquid sun is a material approach to interpreting light. It is, in some sense, recognizing that light is an interaction between atoms. It is a conversation between atoms. It's not this magical bullet of photons that's flying through space. It's two atoms doing something to each other, and in particular to their outer surface, which we call the electron. There's some actual motion happening. And it can be understood because we've very, 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 very accurately described the dynamics of that interaction, of how that electron's being repolarized and what that could mean is just a matter of interpretation. It's a matter of people changing their mind and saying, you know what? I don't think that the electron's made out of math. I think it's made out of something.
And this ties directly to another pillar of the Big Bang, which is redshift. So there's two main aspects of the Big Bang.
Yeah, I love the redshift. Yeah, I love the last 30 seconds of this conversation. So.
Excellent. This is something that we've devoted a great deal of time to, and there's one of my favorite moments actually on the Material Atomics channel was we sat down and we reasoned through. Do you know the three polarizer paradox?
Yes, I made a recent video on it where I argue that actually matter is a wave, and so light is a wave. And so if you just look at the perspective that there is no dual nature to light, and you just consider that matter is a wave, then it explains the polarizer effect as well as double slit experiment and other factors.
And that's similar fundamentally to what we're saying, except that I think we treat matter as being nodes that waves travels through. And this directly connects to the red light shift.
Can I just clarify that really quickly, just to make sure we're clear?
Yeah.
So we treat a wave as an action. So the action must occur in some substrate, and our job with the Material Atomics Project is to give shape to that substrate, to give some material representation to what is it that's waving during these processes, and not only that, but how is it waving, right? Because it's this particular polarization phenomena, and we try to explain that in terms of the motion of the different parts of the atom, how the atom is being deformed in different ways that gives rise at a distance upon its neighbors as this electromagnetic phenomenon. So absolutely everything is waves, but the waves are occurring in a substrate, which is the material from which the atom is constructed.
Sorry, for my audience, can you just briefly describe the three polarizer? I didn't mean to cut you off there.
Yeah, of course. So the three polarizer paradox is as follows. Polarizers are able to transmit a single orientation of light. And so if you take one polarizer that has a grate that it faces, let's say, up and down, it will transmit about 50% of the light. And if you were to take a second polarizer and place it in front of it exactly parallel, then that'll cut down some of the light because there's like more stuff in the way, but you'll still get transmission. But then if you turn the second polarizer to be 90 degrees, you get absolutely zero light coming through that because the first polarizer has allowed light through in one direction, and the second polarizer only allows light that comes through in the exact opposite direction, and so you get no light transmission. And then there's this absolutely crazy thing that happens where if you take a third polarizer and you put it in between them, and it's rotated at, this is important, it's rotated at 45 degrees, then you suddenly get more light that's coming through. And it's this huge paradox because if you have photons as being like little bullets that are being shot around, you're like, what magical thing is happening when you introduce this other polarizer that all of a sudden is allowing more light to come through? And you can go dig down through YouTube and there's all these crazy explanations. But if you treat light as a wave that has to be absorbed by atoms and then re-emitted by atoms, then what you're having at each polarizer is you're having an absorption and re-emission effect. And so the orientation of the middle polarizer at 45 degrees matters because what's happening is that when all of that light that's polarized in one way hits the second polarizer, it gets kind of twisted to 45 degrees, and now it's as if the light that hits the third polarizer is at 45 degrees instead of 90 degrees. And now you have light coming through. And it's like, it's such a simple and straightforward way of thinking about light and atoms because the grating of the polarizer is basically like an antenna.
Mm-hmm.
Like each string of the polarizer, the thing that actually makes it, is a long chain of atoms that are able to rotate in a vibrate.
I mean, yeah, we could get into the weeds about the specific motions of the atoms during conduction and so forth. But Nasi is right. Like the best way to understand light is studying antenna because we understand very, very specifically how antenna function, particularly in terms of how they're being repolarized during the production of light and how that relates to the wavelength and frequency and so forth. And so, absolutely, like the solution of the three polarizer paradox is treating the polarizers as active antenna. They're not just some passive screen. They're actually participating in the relay of light. And actually, like if we extend that all the way to everything in the universe, this relay concept gets us way, way closer to making sense of things like redshift and so forth, because it's not just this, photon magic stuff flying off into the universe doing whatever it wants. There's actually a mechanism available for how it does what it does.
Which is that because it's an absorption and re-emission process, like each time that light travels and it passes by an atom, it has to interact with that atom before being relayed to the next atom. And so when you're looking to the far reaches of the universe, you're not just seeing bowling balls of photons that are getting shot out and traveling uninterrupted all the way from 13.8 billion years ago to your eyeballs or to your telescope's eyeballs. You're seeing an unbroken chain of interactions that stretches from the farthest reach of the universe to where you are. And you lose a tiny, tiny bit of energy at each relay event. And that tiny loss of energy is probably what causes redshift. Like it's not.
You should expect that you'll lose these. Like, look, I'm looking across the room at you right now on a screen, but there's tons of atoms in between my eyeballs and that screen. The thing is, they're neutral atoms. So, mainstream physics would tell us that they don't interact with light. We're saying, no, they do. They do, actually. It's just a less lossy version with neutral atoms. In other words, the signal is being relayed in a very clean fashion between us. But when you're talking about gazillion
13.8 billion light years long, you're gonna have effects. And this is what comes back down where you're like, okay, well, how do you relate this, like the quantum stuff and the field stuff to the liquid sun? And I'm like, I think that it's a slightly larger picture where in order to understand the things that you see when you look out across the universe, you have to have a model for what atoms are doing and how they emit light in order to make sense of what you see, because that's the only signal that we have. There's no other signal that we have except for electromagnetic radiation. And so if you're just kind of like, well, I don't know what it is, it's fields, man. It's like, okay.
By the way, we didn't tell people, but if they're not into the cosmology thing, when light loses energy, it reddens, right? So that's the trick. And the cosmologists point at the reddening of distant objects and say that they're speeding away from us, with the kind of Doppler like speeding, right? It's more of an expansion thing. Actually, they say the universe is actually expanding, so the waves are just elongating, they're getting redder. But there's just a much more mundane explanation available.
Like what makes more sense? That space itself is expanding and the expansion of space is stretching the light? Or is that there's a lot of atoms in the way and interaction with those atoms is causing the light to shift?
I guess I have my own theory on that. You mentioned when light loses energy, it reddens, and we measure that as gravitational redshift, right? So anytime you have light traveling from a stronger gravitational potential area to a weaker gravitational potential area, you're going to have redshift, right? Which we've measured on Earth. And then as it actually goes to another like star, imagine it goes to the sun, like the light from our planet goes to the sun, it will actually be blue shifted because it'll have a higher gravitational potential. So it'll actually shift the other direction, will be blue shifted. So I've promoted a theory as well, that same video I talked about with the linear polarizer, that talks about gravitational redshift, basically making the argument that what we see from the redshift and what we see from gravitational redshift around large objects is exactly the same thing that we've measured here on Earth and we measure from other planets and stars, is actually a redshift. So, because the argument, I believe you're saying, is the tired light argument, whereas you have like a proton in every meter of space, even in the vacuum of space, there's still like one proton. But the argument against that I've heard for tired light is that you would see some sort of diffraction, or you'd see some sort of, it would be blurry, right? The light would be blurry if it's still being re-emitted by all these protons. So that's their big argument against tired light. But my argument that I've proposed is that it's actually gravitational redshift. That if all cosmological redshift is just gravitational redshift, but at a very large sphere, right? As the light expands in a sphere, if we look back, 13.8 billion years, you have to encompass all of the mass inside of the sphere. So that would be all the mass of the universe. And so if you use all of the mass that we know about in the universe, it just so happens to equal the speed of light, right? If you take Hubble's constant, for instance, and you multiply it times the furthest distance we can see, which is around 4360 megaparsecs, it just happens to equal exactly to the speed of light, right? So the amount of redshift that we see per megaparsec times the furthest we can see in megaparsecs literally equals the speed of light. So I guess I feel like there's many coincidences like that, and Unzucker has his own theory kind of related to which I think is the same thing, is that basically it's the redshift is due to this gravitational redshift. But that would mean that you would have to have an ether, right? You mentioned a substrate before, Shilo. I was going to ask you, so what do you think? Is there an ether? Is it required by what you consider of the universe?
Okay. I want to answer that question, but I think we're actually saying the same thing. And so the way that we would interpret this gravitational redshift has to do with the answer to your second question about this ether business. So if I can work my way back to the gravitational redshift via the ether. So what we're saying is that the atoms have an extended architecture. In other words, the medium for the transmission of light, gravity, electromagnetism in general is none other than the same substance that forms the atoms themselves. In other words, the atoms are the ether. They just have an extended furry structure to them. And so when you think about why in the world people didn't take the ether seriously in the last 100 years, it came down to a set of experiments that were designed envisioning an ether that was separate from the atoms. In other words, they were looking for something in between the atoms that they could detect as doing all of the jobs that we would expect of an ether. And we're saying, no, the atoms themselves are the ether, actually. They just have a very rarefied, extended structure to them. So if we go back and start thinking about some of these mathematics concerning gravitational redshift using such a model, it becomes a little more understandable how when these atoms are really tightly packed in with each other and they're yanking on each other really tightly through this gravitational process, which we consider a tensile process where their surfaces are actually merged and putting each other under a great deal of tension, what happens is that the particular oscillations of the atom that are responsible for light, they become gooey and slowed down a bit in some sense. And we have every reason to believe that this would redden the light close to gravitational sources, but there's even better evidence for it with things like what the mainstream would call time dilation, right? So they'll send these atomic clocks up into orbits with these kind of elliptical orbits, right? I think it was actually a broken satellite where they first figured this out, did this test, but the satellite comes, and makes a close pass to Earth, and it's experiencing more gravity. And they say, oh, time is slowing down when it's closer to the Earth, right? Because their clock slows down. And we're like, well, of course the clock slows down because the clock's made out of atoms, and you're measuring time by how fast they vibrate. And their vibrations are being essentially damped by interactions with one another. So of course that's going to be an effect that results from it. It's not some spooky magic where time, the idea that we came up with to measure the rate of change in systems, is itself slowing. It's just that that's the natural output of a clock that's made out of atoms, because the atoms are physically affected by one another depending on their network proximity to one another. So there's very mundane explanations available for almost all of this supernatural, spooky stuff that collaborates to explain everything from the fine grain all the way out to the redshift. And so I think we're very much looking at it in a similar way, that these interactions with neighboring atoms ultimately result in all the phenomenon that you see in from this cosmic structure all the way down to your ordinary everyday life.
It drives me insane. Listen to the ridiculous just the ridiculous mainstream arguments, where they just use all this flowery language and talk about these amazing, like the black holes, like Neil deGrasse Tyson. I listened to him for years, talking about what would happen if you, on the event horizon of a black hole, and like you would stretch, and
that's so much fun.
All these ridiculous. It's so ridiculous. And how difficult it is to just change, to try a different fundamental assumption, just to try an ether based model. They won't even attempt it. Do you know why they just won't even consider it? Or do you think maybe that is changing?
I think that this is going to be a similar transformation to the liquid metallic hydrogen being a type of structured plasma, where I get a lot of mileage out of this one Einstein presentation. He gave a speech at Leiden University in 1920. And when I was reading it, I was struck by the fact that he was presenting on space-time and trying to explain it to people. And he called it a non-kinematic ether. And he was like, I don't really know what that means, but it's apparent in the mathematics that this is what it is. He didn't put it in exactly those words, but that's how I'm interpreting it. And as we've been working on this project, I'm starting to realize that what he meant is that space-time is not the substance in between things. It is the substance of things, which is what Shilo's saying. It's not like...
Or at least represents the motion of the substance between things.
Sure, yeah. And so I think that what Shilo's saying here is that the problem with the luminiferous ether, which was the ether of the olden days that like Michelson Morley tried to detect and they couldn't, but it turns out that they went and they rebuilt a detector in the 1930s that was much larger in this big field, and they actually did detect it, but nobody was listening at that point because like politics had gotten a hold of physics at that point, where the Nazis were coming to power and they were accusing Einstein and relativity as being the Jewish science. And the rest of the world was obviously vocally against the Nazis. And so it was like, oh, you think it's the Jewish science? Well, we think it's the right science. And so the ether became basically like Nazi science. And so we lost the ability to actually reconsider the results of those experiments and what they said about the nature of the interconnection between all things. But Einstein was on it. He was like, there's this thing that's in between everything that's not an actor. It is the place where things happen. And he didn't know exactly how to explain it, but I think that that's what he was pointing to. And I think that as we if people are able to realize that mathematics and fields are descriptions as opposed to explanations, then we'll be able to make this conceptual switch relatively easily. And I think that that's really what I want people to take away from this, is that these are just frames. Like, if you shift the perspective that you have on something, where you begin with the mathematics, and you said something really fascinating about the Ptolemaic model, where you're like, the Ptolemaic model was this really complex thing where in order to understand it, you had to do all these Fourier transforms, and like it was just very technical. And so you had a priest class to explain it. And as you were saying that, I was like, it's fascinating because in order to construct the heliocentric model of the solar system, you do actually have to do the transform, but the transform is used in order to simplify as opposed to make something more complex. Because if you sit there and you look at the stars, they appear to follow the patterns of the Ptolemaic model. But what somebody did is they looked at that and then they made this mental move where they were like, well, hold on a second. If we move where we're looking from, everything is simple. And that's the move that science always has to make, is that you go from somewhere where you're looking at something really complex and unbelievably difficult, and instead of standing at the center of it and just wallowing in your own superiority for being the one who gets the math, you understand the math, you grasp it, and then you make this lateral move where you're like, actually, if you look at it from here, it's very simple. And that's the same thing that's happening here, where they've gotten so enamored with the fields and the maths and all of these massive complexities, Nobel Prizes, where someone has to come by and stand on the outside and say, hey, that's all, like, that math is good. But you can make this subtle mental move and suddenly see it from a different direction. And then everything, the huge new horizons open.
That's a great point, because they were correct. They were correct. Like, if you consider it from your perspective, all of their math was correct. They were accurate. It was extremely accurate, and they could use that math to actually, predict the stars or predict the planets. So then they could actually navigate. So for use, based on their knowledge of the universe, it was completely correct. Yeah, you're right.
And like, relativity is kind of the same way. Like, I use this example that I actually read about. There's this Greek philosopher who wrote a paper. I think it's called 111 Years of Magic in Physics Are Enough. I think that's the translation. But he basically lays out this scene where he gives an analogy for how relativity works. And I can't remember the specifics, but it's kind of along the lines of like, hey, you go to a show at a theater, and let's say we're going to see Peter Pan, and you see Peter Pan fly in from off stage onto stage. Like, this character literally flies in and lands and then flies off. And you ask the audience to reconstruct their perspectives of what they saw. So let's say the audience was in the round, there's audience members everywhere, and they reconstruct all of these perspectives mathematically. And they're like, this is how Peter Pan flew, and blah, blah, blah. Like, these are the specific, like, beautiful, accurate reconstruction of how Peter Pan was flying. And everybody walks out and concludes, like, yeah, we basically proved that Peter Pan was flying. But nobody noticed that there was strings attached to the actor, right? That didn't make it into the model. And so this is a very similar situation that you run up against with mathematics. They can only describe what you see. They can never explain what's happening. That's your job as a thinking human being, is to actually interpret all of this data and make sense of it. Nobody, no computer model, no mathematics is ever going to do that for you. It's your job. And you know, I understand why you want to you want to make use of all this mathematics, especially if you spent 20 years training in mathematics. Like, all you want to talk about is probably mathematics. But unfortunately, that's not enough for us to actually comprehend reality. We have to take it one more step. And there's no great training for how to do that. Like, Nasty and I were absolutely blown away by how little time in the PhD pipeline was devoted towards developing hypotheses and developing theories and what does it mean to interpret data. Like, that's a muscle that you gotta exercise or it atrophies. Otherwise, you're just content with reporting the patterns that you see without having to make sense of them.
We actually only had one course the entire time, which was taught by a professor who just recently died, Mike Sheets, where he would have us read papers and then generate new theories off of the data that was in it and come up with experiments that we would use to test those theories. And that was the one class.
I think that's pretty rare too. I think he was only able to teach that wacky class because he was this esteemed, whatever, laureate. And
it was about, he specifically gave us papers on subjects that nobody really knew very much about. It was like these kind of far out topics because it was first year of grad school. None of us had been exposed to a lot of these ideas. And he was like, read it, understand it, and try to criticize the assumptions and figure out how you can test them. And that was mind blowing for me. And I think everybody else in the class, because you have to have that spirit in order to really understand.
And no, I don't think that's happening at other universities in general. I just don't think that all these scientists who are being cranked out of these PhD programs, they don't have time to do that stuff. They're really, really focused on getting assimilated to their mentor's lab environment, figuring out how they can contribute to the work that's already happening, learning all the maths that are associated with it, and getting a grant, essentially, and getting in that pipeline. And then next thing you know, you're 60 years old, at the end of your academic career, and you never really had time to think about that kind of stuff. And it's kind of tragic. So I don't totally know what the solution to that is either, except for something like what Mike Sheets did. But there is a muscle that you have to exercise in order to interpret data. It's not a given situation just because you learned how to work all of the equations and instruments.
What did Mike Sheets do?
Mike was a famous biophysicist. He developed these really incredible systems for measuring the physical stresses that individual cells exert on their environment. So he made these deformable pillar platforms where he would put individual cells, which would kind of walk on them in these cell cultures.
And then they would take like SEMs of them, right?
They did all sorts of reconstructions based on the mechanical properties of the pillars and how much forces were being exerted on them as a result. And I mean, I don't know his research that well, but from my surface level understanding,
he was a pioneer in basically saying that the mechanics of cells were incredibly important to understand, and that the interaction of cells with their underlying environment was a huge contributor to their behaviors. Which is like a total paradigm shift, because I think that prior to his work, there wasn't a way of actually demonstrating that because cells are very small. And so he had to combine it's the same sort of technique that they use for lithography in making computer chips. And so it was a combination of him being in the right place with the right curiosity, where the technology had finally caught up to being actually able to produce something that gave you a readout for the behavior of cells.
It's interesting. I saw recently, and actually put it in the work I'm working on, that they discovered biophotons, basically that mitochondria in one cell can actually communicate with mitochondria in other cells. They're also noting that DNA, when it actually replicates or repairs itself, it will give off electromagnetic emissions. So basically the argument is that all forms of life, I'm making the argument that all forms of life actually emit some sort of form of non-black body radiation. I don't know, Shilo, what do you think of that? I know you have a background in bioengineering, or
yeah, it's more biophysics. I mean, I was just basically my work was all about just applying mechanical elastic mechanics to molecules and atoms themselves. But with the biophoton stuff, it's super interesting. I mean, we've had a couple of people on our podcast to talk about this, and it's really intriguing. I mean, a simple case can be made that light must be a part of the conversation inside of your body, because if you hold a flashlight up to your arm, like a powerful enough one, you can actually shine light through yourself, right? You could do it with your cheek or something, I guess, more easily, but like your body,
permeable.
yeah, your body is permeable to light. There's certainly, and if you follow our material atomics approach to this, there's a lot of light relay going on inside of your body at all times. And so, the extent to which that's important in biological processes is a completely open book as far as I'm concerned.
But I think that's another one of those things where it's like, okay, well, if biophotons are important, then what is artificial light doing to us? What is being bathed in Wi-Fi doing to us? What is your cell phone doing to you? What is touching your computer while it's charging doing to you? There's Shilo, actually, he always reads Wikipedia before bed. And he started going through the list of pseudoscience topics on Wikipedia, and this is firmly within the category of things that are treated as pseudoscience, but so are other things
like hypnotherapy, Vedic diets. Carnivore diet was on the list of pseudoscience.
It's just like anything that doesn't have a placebo-controlled double-blind study.
Pharmaceutically
yeah, like
sponsored.
You can't make a pill for is considered pseudoscience at this point. But I think that there's a lot of these questions where if you have to really reconsider your environment from the top down, and you have to really re-examine, well, like, what does it mean to stare at a screen for hours and hours a day while you're doing your work, or you're doing video editing, or you're talking to your friends far away? It just suddenly starts to undermine the entire foundation of everything, in the same way that, the story of the radium girls?
No.
So back in the day, when they first discovered radioactivity, it was viewed, before they realized how dangerous it was viewed as a novelty item. And so they made like uranium glass dishware, which you can still collect. People have it where it's dishware that glows in the dark because it has small amounts of
uranium. It's very beautiful.
Yeah.
It's amazing. But they would manufacture watches with glow-in-the-dark dials.
Yeah. Isn't that how Marie Curie died, I think?
She died just, I think, from the sum total of all the experimenting that they were doing before they understood. I don't think it was specifically radium, but it might have been. But the radium girls were working in a factory in New Jersey where they were painting watch faces with radium paint. And in order to get the paint brushes to be sufficiently fine to do the small lettering, they would lick the paintbrushes. And they all got terrible facial cancers off of it years later. But I'm like, if you live in a world where literally everything from top to bottom is screwing with your natural rhythms because it is emitting huge quantities of electromagnetic radiation, how do you even begin to look at cleaning that up? It's one of those things that's easier not to stare at.
It's been a huge issue in the UAP world as well, because we've seen a lot of human effects. They even added it to congressional bills. They talked about human factors or human effects, negative human effects. Gary Nolan's done several studies on it. He was approached by the CIA where he said it looked like Havana syndrome. So people had issues similar to Havana syndrome, like, essentially negative growths in their brain, really, terrible, terrible things. But I guess what is your looking back on when the science seems to have been, I don't know if it's been suppressed, or when the train went off the rails, when do you think that actually happened with science?
I think it's always going off the rails. I think that's just par for the course. I mean,
I have a discrete moment.
Hit it.
I think that it is when Newton came up with calculus and tried to explain the cause of gravity and couldn't, and was basically like, it's not the scientist's job to figure it out. Our job is to describe. He has a really famous quote so Newton's story is really crazy because he writes the Principia and then he writes Optics. And in the appendix to the second edition of Optics, so this is many, many years after he writes the Principia, he comes up with all this mathematics. He writes an appendix that is kind of an update on everything that he's learned. It's called the General Scholium. And at the end of the General Scholium, he's kind of losing his mind about the fact that he's been studying all this stuff and he still can't explain what's causing it, right? He's kind of leaned into this corpuscular model of light, but the corpuscular model of light doesn't really work. He's been trying to explain gravity, but he can't figure out how to come up with a model that actually does it. And so it's just this rant, this stream of consciousness, just unbearable frustration of this guy who's considered to be the most brilliant person in the world who can't figure it out. And the way that he deals with it is he's like, it is not the job of the experimental philosopher to come up with explanations. It is our job to measure, parameterize, and to produce the mathematics. And he says, hypothesis non fingo. I make no hypothesis about how gravity works. It's not the time to figure it out. Someone will figure it out later. And that is buried deep in an appendix to like a second edition to optics. And no one really focuses on it. But I think in that moment, he's expressing this vibe, which is, we have no idea how this stuff actually works, but the mathematics is incredibly powerful. And so he comes up for the first time with the mathematics of motion. Like, you got to think about how crazy that is, because prior to this moment, everything is just like algebraic and geometric. It's static systems. And yet everybody knows that in order to develop the next level of technology, you really have to have mathematics that can deal with motion and the fact that things change. And he lays it out, and everybody's like, okay, this works. And he's really smart. And he says it's not our job to figure out how it works. And you can build so much with it. You can do incredible things. And then when we discover electricity, Newton is this ghost in the machine who, when people can't figure out what causes electricity and they can't figure out like why electric fields are able to do things at a distance, they can point back to Newton and they're like, well, he didn't figure out gravity and it seems like that's okay. So maybe we don't have to be smarter than Newton.
Yeah, can I just substantiate what I said about it always going off the rails too? Like, what I mean is that our goal here, like all of our work circles around this, what we believe is a coming revolution in science. And our goal is not to replace one crappy dogma with another crappy dogma. Our goal is to really re-centralize the idea that our ideas are always in flux, kind of like how you opened up this conversation today. We're always going to learn more, and we're going to need to have a flexible science that's capable of entertaining multiple theories at once and comparing their merits on the merits, and and their deficits, and looking at it objectively, dispassionately, and being able to move forward. Like, if science is going to be a career structure for people, it needs to be the kind of career that doesn't depend on your theory being the right theory forever and all of time. That's just not going to work. And so we don't advocate, even with the liquid sun, it's like, maybe there's a better idea down the road too. But this makes a lot more sense to us at this moment. And at least it should be in the arena of discussions with respect to all of these problems, from fusion to cosmology. We need to have a culture of science that's capable of having these kind of discussions, and we don't right now. And so that's what it's really about for us.
I wish you had a microphone you could drop right now.
Yeah, you mentioned the Big Bang, right? That's basically going to be the main focus of the Demystify Sci conference this summer. But you can't say the Big Bang didn't exist. You can't even propose any alternate theory for like the ether, or that redshift is coming from gravitational redshift. You're basically thrown off the stage. I think Sean Carroll said that is basically, if you say the Big Bang didn't exist, we don't let you on the stage, right? That is the current paradigm. Same thing as if you say that non-human intelligence is here, right? If you even go with the assumption that maybe all these hundreds of thousands of people are not just insane or crazy, maybe these are credible humans who have seen something, right? Maybe we don't understand the perspective that they're coming from, but we could actually even just try the assumption. What happens if we assume that they're not lying? Where do you get at the end? But I wanted just kind of finish on two main points you said. You mentioned electromagnetism and gravity. I think it is amazing that we still don't understand those two things really. And Newton, you mentioned Newton. I think he was amazing as well, because he said that the same gravity that affects us, it affects the moon. or the sun, which is just amazing if you really consider that. But I guess my work that I've proposed suggests that gravity and electromagnetism might be fundamentally linked, or they are linked through energy density relationships, kind of what you mentioned there about the density of atoms. Do you see any promising avenues in physics for unifying electricity and gravity, beyond the standard model? Is that what you're proposing in your own theory or work?
That's exact. That's exact. I mean, the specifics are nuanced, but look, if this medium of light and gravity is actually the extended architecture of the atoms themselves, then gravity and electromagnetism are just two different, let's say,
Motions.
pressures or motions within that material. So gravity being this more aggregate tension that results from a proximity effect where you're more connected to the things that are closest to you. And so there's more tension in that system. Whereas electromagnetism actually has to do with the particular rotatory pressures at the surface of the atom that are happening, the way that this material disperses at the surface and puts tension on its neighbors as a result of it. It's more of a dynamic process, whereas gravity is a static process. In other words, you don't have to be moving to feel it. The atoms could be at 0 Kelvin with no motion and still be subject to gravity because they're still connected to their neighbors. But electromagnetism is just a different motion of that surface. And we go to great lengths, both in this book we're working on and a bit over at our YouTube channel called Material Atomics, where we animate some of these processes and give our best shot at interpreting what the equations say that the atom's surface is doing in its extended architecture. So yeah, absolutely. And I actually think about all the time, taking these UAP reports seriously, what would it look, or even just imagining how the hell are we going to get to other star systems if that's our goal, And I see there being a potential avenue for manipulating that interconnected web in such a way that you could detach an atom from the web, at least hypothetically, theoretically. I'm just going like full on speculation here. If that could be done, then you would perhaps, that atom would no longer be subject to the same pressures and restrictions necessary. In other words, it could overcome that material boundary of deformation of that material, which we call the speed of light, essentially. So, by understanding a material explanation for these basic atomic phenomena like gravity, like electromagnetism, we might get ourselves closer to understanding how we could manipulate the basics of atoms in a way that would be productive and allowing us to travel to the stars and allowing us to make sense of how other people might be doing it in other solar systems. But without that material understanding of the atom, I think we'll just be lost in the math forever.
And if I can add something to that, I was thinking about this a while ago when we were trying to figure out ways to justify why this reimagination is important. Because you go to an engineer and you're like, hey, we might have a really poor understanding of what electricity and magnetism is. And they're like, yeah, so what?
So what?
And on some level, they're correct because cell phones, airplanes, Zoom calls, MRI machines, like we have all of this stuff that works really well, despite the fact that we're missing these models. But then I go back to the roots of biology, which is fundamentally where my roots lie. And I realized that before we had DNA as a substance for heredity, we had statistical biology, where there was a school of, they called themselves the biometricians. And they basically thought that it was enough to look at populations and to look at the distribution of traits in the population to create mathematical models of the likelihood that a trait would be inherited in any situation, and that it didn't really matter what was happening inside of cells. Like you could predict the future sufficiently with the mathematics that describe your system with enough parameters that the inner workings were irrelevant. And they were poised directly against the people who were doing absolutely arduous biochemical work to figure out what the hell was inside of cells. Like the guy who came up, who first described the nucleus, would go to a hospital where he would collect bandages of pus, filled with pus from infection drainages, and he would isolate the white blood cells from those, and then he would fractionate the cells, and he determined that there was this like phosphate enriched substance in all of the cells that he thought was the medium for inheritance. And then it took decades and decades of just incredibly difficult work for people to figure out that there was DNA, what its structure was, and then all of this downstream work that figured out, translation and transcription and the way that proteins are related to it. And we have molecular medicine on the basis of that. We have the ability to now go in and say, look, this person has an incurable disease, but their incurable disease is caused by the deficiency of this one protein. And we can synthesize this protein in the laboratory because it's not made out of mathematics. It's not made out of the biometrical field or the genetic field. It's a substance that is made out of amino acids and atoms, and we can make it and we can give it to them and they work. And so if we stand on the precipice of physics and we're like, the math is everything and we don't need to understand what fields are, we stand on the same precipice that we stood on with biology more than a century ago, where there's people who are saying, no, we don't need to know what's down there. We just need the math. And I think that the proof is in everything that came downstream, where it's like, well, no, I think we actually might need to know what's down there, because if we want to get to the next level and not be forever just playing statistical games, this is the only way. With getting to other star systems, with fusion technology, with, I don't know, anything that you can think of, I think that it comes down to not just stopping at the math and saying that, well, it's just fields. They're kind of doing weird stuff.
They're just separate fields that don't interact with each other, which just sounds it's so ridiculous to me. But yeah, so UAPs, when I look at it from the perspective of what if UAPs are real, or if they are a physical thing, then it looks like they all are silent, right? They don't seem to have noise at all, and they don't create sonic booms. So like you mentioned, Shilo, they do seem to be separate from our, at least the environment that they're moving through, right? They can go hypersonic speeds and not create a sonic boom. So they're in some way not interacting with that matter. And what always seems to be interesting is they will be symmetric usually, and there's always light. So it seems like they use light as some sort of tool or manipulation. They'll either shoot light beams that do things, or they will themselves be cloaked in light. What we see is there's gravitational shift. I'm meeting with the Tedesco brothers next week, and they argue that they're able to actually detect gravitational lensing around these objects based on radar returns that they can pick up from ships that are behind the objects. So it may be even a way that we can use gravitational lensing to identify these craft. But the other thing is, people always seem to, when they investigate this or UAPs for a long time, they end up in somehow falling into the woo, which is basically consciousness, where somehow, if you look at every pretty much alien encounter ever, I think, is telepathic, right? They're communicating telepathically. If an alien shows up at your door and just starts talking like normal, you should be very suspicious, essentially, if you know the mythology. But in this case, if based on your theories and everything you've encountered, would this change everything? Would it allow telepathy? If we're talking about an ether, would it allow astrology to be correct? All these ancient kind of paradigms or thoughts that we had from ancient, all the religions. Essentially, you're when you pray, you're essentially communicating telepathically with a non-human intelligence. And if you look at all our cultures based on the stars, based on astrology. So I guess based on your theory or what your suspicions are, would that allow telepathy? Would it allow astrology to be correct?
I mean, if you think about it, when we already have telepathic abilities with these little black mirror things that we have in our pocket, right? We can, and that would be essentially magic to somebody from 500 years ago if I just picked up my phone and called somebody on the other side of the country, right? I'm talking to somebody who's far away, and I'm using light to do it, actually, which is really interesting. Like when you talk about light being associated with these reported objects, if they are disconnecting from the local atomic network, you would expect that that slack would be evidenced in some sense in the light network, especially the way that we understand light as being this conversation between neighboring atoms. So that makes a lot of sense. When it comes to improving our ability to telecommunicate with people, why shouldn't we continue to improve that and shrink that little black mirror down to the point that it's not even evidenced in the conversation at some points? I fully expect that, if we manage to not wipe each other out in the next 1,000 years, that will become an invisible piece of the puzzle for anybody who's coming to, any outside observer watching humans talk to each other. Like, you're in Portugal right now. This is freaking crazy that we're even doing this. Now imagine it without all of this hardware, because we found a way to shrink it down or in some way make it less of an obstacle. I fully expect that will be possible if we, like I said, if we don't start World War 4, 5, 6, and so on.
I have a much crazier theory about this, actually, which I don't think I was thinking about it as you were talking, where there's this question in human evolution, which is called the sapient paradox. We become genetically modern 300,000 years ago. And then for the next 250,000 years, we just kind of faff around doing whatever it is we did in prehistory. And then all of a sudden, in the course of 10,000 years, we start to do all of this abstract stuff. Like, we start to paint, we start to have ceremonial burials, we appear to develop an abstract relationship to the skies, we probably form religion for the first time. And it's this huge question of, okay, well, what happened? How did that possibly come about? And a lot of anthropological studies seem to think that there was this process by which we started to recognize our own thoughts at some point. And at first, we heard them as the thoughts of gods, where, like, over the course of your day, you'll have this feeling of like, oh, I'm hungry. And maybe you'll even vocalize it to yourself as I'm hungry. And in prehistory, anthropologists assume that that would have been taken as the voice of a deity who is telling you, like, go eat. The idea of the I as a cohesive entity didn't exist yet. And we actually had a really interesting conversation on the podcast just a little bit ago with a guy, we haven't released this episode yet, who's like, if there's really, really good evidence for there being some kind of cult that developed ritualistic ceremonies that brought them to the verge of death, and in the process of this near-death experience, they were able to separate out the fact that there was somebody who was inside of the body, like an I, an ego, a consciousness, and the body itself. And so it was this first sense of there being an actor. And so the voice of God in that moment became the voice of the person. It became the I. And the downstream effect of this is that this culture was incredibly effective at doing stuff. They were able to figure out agriculture, they were able to figure out complex social structures, they were able to probably form alliances with the people next door to them. They were able
They got really good at war and slavery too.
Probably.
everything. They did all the human stuff. But the move was a mental move of being able to say that there is an I, to be able to communicate something that was already there, but not yet formalized. And so I'm like, is it possible that the ability to communicate non-verbally, this sort of telepathic stuff, is another mental move that requires a culture to develop a technology for inducing it in such a way that they're able to reliably spread it to people? That seems like it could be the next level of human evolution, the same way that everybody right now thinks that the emergence of the I and the separation from God was the step that created everything that is in front of us right now.
It's worth pointing out there is some intriguing evidence about this telepathy business too. And I know there was this huge podcast called Telepathy Tapes that came out last fall. And I'm really intrigued by some of the substratum of that work. There's a scientist behind that work named Diane Powell, who's actually coming out to our house on Friday. We're going to film a live podcast with her.
Amazing.
And she we had coffee with her once a couple months ago. And she seems to think that the telepathy tapes contained the worst evidence. In other words, she thinks that she has much, much more strong evidence for these nonverbal autistic children being able to somehow communicate in ways that we don't understand. And so I'm super stoked to unpack that because the reports are absolutely extraordinary.
Have you had Dean Radin on your channel?
We have, yeah.
Mhm.
Yeah,
Okay.
I had him as well, and he has really compelling data as well. Interesting as well. Initially in his career, he worked doing the same kind of, telepathic, I guess, studies, if you will, but in a classified scenario. And he said they were very open minded, like, yes, of course, but he didn't want his work to be classified. So he actually went into the civilian world, and he said it was much more stigmatized, essentially.
Yeah, I think that there's just a certain openness that you have to cultivate. I think that the universe is so wild and crazy and full of things that we don't understand. And it's really easy to look at how screwed up everything has been, and the institutions are crumbling, a new age is being born, and it's really easy to get caught in the fear, uncertainty, and doubt of that transition. And I think that it's probably a lot healthier and a lot more fruitful to just be inundated with awe. Like, we stand on the shoulders of giants. We have the entire, every single one of us is linked back through time to so many organisms that fought to be born. And we are here and we have the ability to look out onto the world and try to piece it together and try to understand how all of this works.
And that's the key, by the way, to the like. You don't have to even like look. You can look at telepathy, and even if it proves out to be absolutely extraordinary and evident that there are telepathic interactions, it doesn't mean it's because of magic. That's really important to remember. Like, there's a way that's happening, and we can understand it. And I guarantee you, if it does prove out to be evident, there's atoms at the heart of it, and there's some atomic process going on, and it's going to be amazing to figure that out. It doesn't have to be mystical or science. Like, that's not the option that you're faced with new phenomena that you don't understand. So.
Amazing. And so we'll be at the conference Demystify Sci. I'm super stoked. So we'll have Eric Lerner will be there. We have Alexander Unzicker. I've had him on the channel. We'll have See the Pattern. So I watch all these YouTube channels, actually. I'm like secret fans of these channels and extremely stoked to go. And so I talked Simon Holland into going. Actually, I told him about it and talked him into going as well. So we will be there. So I'm very excited. Can you give some dates on it, some information, so if people want to come, they can come meet all of us and take part in these conversations?
Yeah, it's going to be June 12th to 16th. We're holding it in Sesimbra, Portugal. It is a seaside resort that is maybe 40 minutes outside of Lisbon. It's going to be 4 days of talks, panels, discussions, opportunities to meet people that share your interests. I think that this is actually the most exciting thing, which is that every single person who's watching this conversation who has gotten to this point, I would bet is probably the only person in their social circles who is obsessed with this stuff. And they go out in the world and they try to tell their friends about it, and they see their friends' eyes just glaze over as they try to talk to them about the Big Bang. And it's just such a sad state of affairs. And at our last conference, we held it in Austin last year for the eclipse, everybody got into the room and realized that their friends were there. Like, these are the people that share your interests. These are the people that are thinking about the same questions that you're thinking about, that are obsessing about the same topics. Everybody had brought like papers to share with each other. And before we even sat down for talks, the room was buzzing. Everybody was exchanging information about their favorite theories. I had several people tell me that they had made lifelong friends within the first day. It is such an incredible opportunity to get together with people who care about the same stuff that you do. And the people that we've invited are all speakers on subjects that you care about, and they're deeply interested and interesting, and they'll be there to socialize with. It's going to be a pretty small event.
Yeah, and we also invited a bunch of academics too. Let's be clear about this. Like, not only did we, invite all of our favorite thinkers on the fringes of science who we think have ideas that are going to change the world, but we also invited people who understand the mainstream perspective really well and can ask all the right questions. You know, early career scientists in cosmology, people who've been staring through telescopes their whole lives, you know, and that's what's, I think, going to make it a really unique and historic event, is that it's not just this cloistered one-way perspective. There's going to be potential for real growth in everybody's minds as a result of that. So I think it's pretty unique and awesome. I can't believe there's any tickets left, actually.
I think you picked an amazing spot too. Like Portugal in June is just amazing. It's so beautiful, and the tourist season hasn't really started yet. So the heavy tourist season starts July and August. That's when you don't want to go. So the weather is perfect. That's in Setúbal. It's right just south of Lisbon, and I'm not staying at the fancy resort where it's going on. I'm actually staying at a little Airbnb. So it's, you can easily get an Airbnb, super safe. It's beautiful, right on the beach. Yeah, and then from there you can go anywhere. Yeah, you can go visit north. You know, go up to Braga and Porto if you want. I recommend Coimbra. And you can go south. Well, I live down in the Algarve, is down in the south. You know, that's where everybody goes for vacation. But Portugal is beautiful. Yeah, if you haven't gone, it's amazing, and it's really easy to get there from the East Coast. You know, you can fly right into Lisbon. The airport's right in the center of the city, so I highly recommend it. Yeah, if anybody goes.
If you don't want to stay at the resort too, we've got multiple tiers. Like you can just buy a much cheaper admission to the event itself. You can come to the dinners at a different tier, and then if you want to stay at the resort, you can do that too. But we're absolutely trying to open this up to everybody's budget. As long as you can get yourself to Portugal, there's a way for you to go to this conference.
Yeah, it'll be amazing. So I'm really looking forward to meeting you guys in person there. I'm gonna pick Simon up from the airport, and then I'll drive him there. Nice. And so we'll meet you. And I'm super stoked. Anyone else in the audience or watching? So come out to Portugal. I think we're gonna have a great time. We're gonna solve it. We're gonna figure out the whole answer. You know, Big Bang not true, and we're gonna find the final theory of everything. I'm just saying it right now. I think this is it at the conference.
Even if we don't, at least we're going to set up a new motif for how to go about that. You know, like this just seems, it's much more in the spirit of the original Royal Society. We're going to get together, different ideas, and we're going to discuss them in a way that doesn't involve throwing coffee in each other's faces. You know, we need a new productive approach to science as a whole. And we're trying to
build it.
Trying to make it happen.
This is the future. We're making it.
All right. Well, thank you guys so much for coming on the show. And please, in the audience, hit the like button. Go check out DemystifySci. Come to the conference, like we mentioned. Subscribe to my channel to get more talks like this, as well as other things on UAPs. And then you can always support my work, patreon.com/Chris Lehto. So have a great rest of your day. Thanks for being here.
Thank you so much.
Thank you, Chris. Bye, everybody.
Bye.